Okay, hello everybody. Today we'll be covering most of chapter 23. We're going to be talking about different techniques to help support ventilatory support. The first one that we're going to be talking about is going to be APRV. Hold on, my slide's being goofy. My computer's being goofy. There we go. Okay, so APRV. So other names, it could be referred to as bi-level or bi-level, meaning bi-level positive airway pressure, kind of as a BiPAP, because it's basically two levels of CPAP. It can just be called different things. On the screen here, CPAP with release, intermittent continuous positive airway pressure. It depends on what type of ventilator that you're using. In Europe, it is called BiPAP, or bi-level airway pressure. Draeger was actually the first vent to offer APRV. It is also on the servo I, called bi-vent. The Puritan Vent at 840 calls it bi-level. However, you can do APRV with bi-level as long as you have your inverse ratio at least 4:1. And then the 980 also has APRV, as well as the Hamilton G5. Alright, so basically it has, like I said before, two levels of CPAP, okay, and allowing patients to breathe spontaneously at both levels. It provides a moderately high level of pressure, which they call P high, and then P high is occasionally interrupted for brief periods of time at a lower pressure called P low. And that time where the P high is kind of turned off, I guess, or not really turned off, but you come off of the P high, is called your release time. Okay, so then you also set a time high and a time low, but we'll get into more details as we go on. Okay, knowing that the main goal is to recruit alveoli and promote oxygenation. It's not really quite as much used for CO2 elimination. We get into situations where we do allow permissive hypercapnia, especially with severe IDE ratios, very inverted IDE ratios. You may end up having to settle for pHs. They generally try to keep them above 7.20. Okay. The next slide kind of gives you a little bit of a diagram, and this is out of your textbook. So again, this is coming from chapter 23. So as you look at this, you can see those two levels of CPAP. You have the high level and the low level. Okay. The second one, the first one you just have a baseline of 0, and on the second one, the one below it, it looks like you have maybe a CPAP level like 5. Okay, so you maintain a certain amount of time at that high level, and then it releases. You're down to your low level, and then back up again. But all during that time, the beauty of it is to be able to still spontaneously breathe, which then hopefully the patient isn't going to require as much sedation, or definitely, obviously we don't want to paralyze them, because we still want them to be able to breathe spontaneously. Just kind of another little diagram here of what's going on. You can see the spontaneous breaths. This is a screenshot from the servo I ventilator, and this is on page 488 of your text. Okay, so some of the different advantages. Actually, let me go. I don't know if I can go back. I don't think I can go back. Let me pause. So if you take a look at that, if your textbook on page 488 rather. Sorry, I'm trying not to make too many spoofs, but I always trip on my tongue. You guys know that. Anyway, so like I was saying, it is designed to provide 2 levels of CPAP, allowing spontaneous breathing at both levels when that spontaneous effort is present. So your P high, which can range anywhere from like 15 to 30, is kind of more like really like your baseline. That's the one where you want to kind of keep it at. Okay, that's what's helping increase your mean airway pressure and increasing your oxygenation. So that then is interrupted with a brief time during that P low time. And that again can range from 0 to actually up to 15. So that's considered the release time. That is your T low. Okay, so both the high and low pressure levels are time triggered and time cycled when spontaneous efforts are not detected. So when we're looking at some of the different advantages, again, it preserves spontaneous ventilation. It does this because the active expiratory valve is floating open, kind of floats open, which also helps have lower pressures. So pressures are lower than during that spontaneous breathing time, preventing pressure buildups. So it also can provide better ventilation perfusion matching. It does this by preferentially providing ventilation to dependent regions that receive the greatest blood flow. It improves gas exchange and lowers PIPs in patients with ARDS compared to patients receiving volume control, and it requires less sedation. Some other advantages here: it requires a lower minute ventilation, which then shows a reduction in the physiologic dead space. It is also noted to increase renal perfusion and function when the patient's able to breathe spontaneously. So investigations showed that APRV produced a lower PIP, better oxygenation, less hemodynamic compromise, and better gas exchange than conventional ventilation in the treatment of ARDS. Also remembering, I just said about keeping that renal perfusion going when spontaneous breathing is maintained. So the other beauty of having the spontaneous breathing happening is that it helps prevent atelectasis by having the diaphragm be active. Okay, and this might also help prevent atrophy of the diaphragm. So that's a really important thing, why they want them to still be able to breathe spontaneously so the diaphragm doesn't waste away. However, it does have its disadvantages. Because it is basically pressure targeted, the volume delivery is then dependent on lung compliance, airway resistance, and spontaneous effort. Okay. Also keeping in mind that it does not completely support CO2 elimination. So with COPD patients, it might not allow sufficient expiratory time. Not all ventilators offer APRV, and of course there is some limited experience with staff, so it's kind of up to us to kind of promote it when we see that there's good indication for it. So we look at some initial settings. Okay, the conventional mode that they're on with the regular ventilator can kind of serve as a guideline. So what some of the settings that they're receiving on the conventional mode of ventilation can kind of give us a little bit of a guideline. So when we're looking at the high pressure, or the P high, that's again, remember controlling the upper level of the CPAP, or otherwise known as your baseline CPAP. So we can either use the previous plateau or mean airway pressure on the conventional ventilator. So whatever your previous plateau was, kind of the range of where you were at, or your mean airway pressure, can be served as a guideline as to where to set your P high. Again, it's usually set somewhere between 15 and 30. We try to stay below 35. Then your P low, that is your release pressure. And ideally, if they can have that at 0 would be great, because this then allows for unimpeded gas flow and a rapid drop in pressure. Okay, so they kind of like to try to have the P low at 0. Remembering that the delta P, or the P high minus P low, the greater the gradient, the more rapid the expiratory flow, and the higher the tidal volume. And then your T high, or I'm sorry, your high time, which would be, which would be T high, yes, I was right, is the duration of time that you spend at P high. No, it gets kind of confusing. And then your T low then is the time that you spend during that release time, or at your P low time. So basically, the time that's set at T high plus T low equals your total cycle time. Okay, so for example, I have some example settings that I thought I would just talk about. So for time settings, if we're looking at a T low, okay, of being 0.5 seconds, and our T high at 5 seconds, so that T high, that's where we're spending most of our time, which is at our P high. We have a total cycle time then of 5.5 seconds. Okay, so that gives us our total cycle time of 5.5 seconds, which if we look at the IDE, that's either 5 to 0.05, I'm sorry, a half of a second, a 5 to, 0.5, forgot my decimal there, or it is a 10 to 1 basically, okay? So that would give us 60 divided by 5.5. Again, you're taking 60 seconds divided by your total cycle time, which gives you then about 11 breaths per minute. Okay. We want to make sure that our T high, that the time that we set at that high peak, high P, is a minimum of 4 seconds, and that's what it needs to be considered APRV. So your I to E needs to be at least 4 to 1 to be considered APRV. Your T low, your time low, is often set at about 0.5 to 1 second. Typically about 0.8 seconds is kind of like a ballpark. So you want to be able to generate regional intrinsic PEEP and enhance alveolar recruitment. Keeping in mind, if your T low, your time that you're spent during that release time is too long, it can actually interfere with your oxygenation. Because what happens is that the lung units then collapse. The ones that you've recruited during your pressure high or your T high during that higher level, if you let it go for too long, you're gonna lose what you've gained, basically. Okay. The textbook also notes that in actual practice, RTs tend to rely on the expiratory gas waveform. So when expiratory flow during a release period is about 50 to 75% of peak expiratory flow, then the airway pressure should be allowed to return to P high. There are some more videos too that kind of talk about that, but again, that's just kind of adjusting how long you should be at that T low. And I have some videos for you to watch at the end of this for APRV. Alright, so again, the the respiratory rate then is equal to whatever the T high and T low settings are. So you take the total cycle time of whatever those seconds are set, and you divide that into 60, and that'll give you your respiratory rate. The tidal volume basically is determined by the difference between your P high and your P low settings. Also keeping in mind that the tidal volume and the flow of delivery is definitely dependent on the lung characteristics, also the patient effort, and the pressure gradient. Okay, the higher the gradient, the more rapid the expiratory flow, and the higher your tidal volume. Okay, just a couple more examples here of some initial settings. Some of these I did talk about, but I also added a few comments here. So when changing a patient from a conventional mode, the conventional mode settings can serve as a guide again. So you can look at either the previous MAV or plateau. It's kind of a little review of what to do your P high. Again, P low, 0 would be ideal. A minimum of 4 seconds on that T high, and where your T low should be. So your T low is set on the basis of the patient's pulmonary condition. So just kind of see, what type of patient you're dealing with and what works out best for them. Too short of a T low, short T low is appropriate for your ARDS patient. So you do want a short T low, so probably on the lower side, like that 0.5 or to 0.8. Again, I already mentioned this, too long a release time can interfere with oxygenation. So the T low settings can vary among your patients and should be performed with caution and careful monitoring. Keeping in mind, if your P high or your high CPAP is less than 30, then the spontaneous breath can actually then be supported with a pressure support. Okay, but the plateau should still not exceed 30 centimeters of water. So you can also add pressure support. And Gary from Puritan Bennett or Medtronics, he actually has come to our school before. The shorter video, he does a lot of education on the APRV and on the Puritan Bennett. Unfortunately, with us being not in class, I can't schedule any of these, so you have to kind of rely a little bit on YouTube. Also, remembering we may have to allow for permissive hypercapnia. All right, how do we adjust the ventilation or oxygenation? So if we have to make changes on these vents, what do we do? So the ventilation and our CO2 are determined by the release time and the tidal volume exchange during that T low. And patient spontaneous ventilation is huge. It's a big part of it. Okay, so if we are, so we really want to make sure that our patient still has spontaneous respiratory rate, spontaneous effort. We do not want them too sedated. So if we have a PaCO2, I believe I have this on a slide coming up, so I'm actually not going to talk about this right now. If we're adjusting oxygenation, we can improve that by increasing our P high, or of course our FiO2, or consider proning. Okay, and then discontinuing once obviously the patient's lung condition has improved and we've got them down to hopefully 50% and a reasonable amount of PEEP. And we'll kind of talk briefly about how you kind of stretch and drop, is what they call it, for weaning APRV. So talking about reducing support, so what we're going to do is adjust your P high and your T high. So you start reducing your P high. Okay, it should be reduced to about 2 to 3 centimeters of water pressure at a time. and then your T low time is lengthened. So eventually the two pressures are going to meet. So your P high is slowly decreased until it meets your P low. So then you're just basically at CPAP. Okay, so your P high and low pressures are intended to meet at the desired baseline. So, maybe you'll compromise at like 15 or 12 or something, and that would be like a CPAP level. Okay, here was the things that I wanted to talk about as far as adjusting some of your values when you have to make changes on your bed depending on your CO2 or your PaO2. So keeping in mind, remember that your delta P, or the difference between your P high and your P low, is your tidal volume, and that the greater the gradient, the more rapid the expiratory flow and the larger the volume. So if you want to decrease your PaCO2, you're going to increase your T low, okay, you're going to increase that time, or increase your P high, okay. So you want to bring down your PaCO2, okay, so you're too acidotic, your PaCO2 is too high, you want to increase the T low time, and you want to increase your P high, so we end up giving a bigger volume. If you want to increase your CO2, you're going to decrease your T low, okay, that's going to make you retain more CO2, because you're not allowing very long time on that T low, or you're going to bring down your P high, so make a smaller gradient. Again, changes in your PaO2, you may want to increase or decrease your FiO2, possibly increase your T high if you want to increase your PaO2. Okay. But being careful, being mindful that with increasing your T high, because your T high, your time and your pressure high combination, a higher pressure for a longer time is going to increase your MAP, which you want to do to a certain point, but you don't want to overshoot it, because it could adversely affect your cardiovascular system. It could bring down your blood pressure and your cardiac output, which is going to be bad in the long run. You're not going to have volume there. Okay, so these are the two YouTube video links. I want to say the first one is about maybe 40 minutes or so. I can't remember. I watched it last night. And then the second one is from Gary, and it's only about maybe 10 minutes. So I want you to watch these videos, and after you're done, I want you to start a discussion thread, and I can start one just to I want to know what your biggest takeaways are, or just any type of questions or discussions that you want to have regarding these videos, and you will be graded on participation in the discussion board. So for this day's attendance, I'm going to count that for attendance. You still also have a worksheet, a review study guide that I posted that covers APRV, high frequency, heliox. That one's already up on Blackboard. Okay, so we're continuing on. Now we're going to be talking about high frequency oscillatory ventilation. Unfortunately, we're not able to make it up to Good Samaritan. I'm really hoping that once things settle down and we get back into the classroom, even if we're doing CV diagnostics, at the time I know that Justin would allow us to take a little field trip up to Good Sam's and have Marty go over the oscillator with us. It's a pretty impressive little machine, and it's great to see it in action versus just kind of talking about it, because it's so unique. And also he talks about nitrogen too, which would be helpful. So let's keep our fingers crossed that things here will pass, and that we'll be able to get a chance to go up there. So the oscillator is kind of a little different bird. Basically, the oscillations are produced by a piston in the 3100B. There's also a 3100A, which is designed for neonates, but the 3100B is for adults. So the pressure is positive in the airway during the inspiratory phase. I'm just going to kind of give you a little basic concept kind of knowledge, I guess background knowledge or whatever, before we kind of dig into it a little bit deeper. So the pressure is positive in the airway during the inspiratory phase during that forward stroke of a piston. So if you think about it, it's kind of like an old speaker, an old, it has a diaphragm in it, and so the diaphragm is a diaphragm-shaped piston that is magnetically driven, like a stereo speaker. So like the old stereo speakers, the ones where you saw the big circle inside of them. So so the pressure is positive in the airway during the inspiratory phase, or the forward stroke of the piston, and then negative during the expiratory phase, during the return stroke of the piston. Okay. Gas is oscillated then back and forth by the action of the diaphragm, so that it actually moves back and forth, and you can see it when it's running. The amplitude of the wave, so like the depth of how much is going on, which is the power, is set by the power control, and determines the forward and backward displacement of the piston, which then determines your tidal volume. So that's kind of the sort of the basic concept behind it. Okay. High frequency has been used for some time in neonates, but we're also using it to treat adults. So it's used to recruit the villi by maintaining a maximum level of mean airway pressure, and it keeps that pressure in there, so it doesn't allow then that repeated collapse and reopening of the villi, and that's what they have found is doing the damage. That's the ventilation-induced lung injury, is by that open and closing of the villi. So it just kind of maintains that pressure, kind of the same concept as APRV, by keeping that high CPAP or high pressure in there for a prolonged period of time. So it uses high MAPs, low tidal volumes. It uses a high respiratory rate or frequency, which they actually refer to as hertz, and we'll talk about that coming up in a few slides here. So it reduces the risk of ventilator-induced lung injury. So the mean airway pressure, sometimes the book talks about as maximum airway pressure, directly then is what affects the PaO2 by changing the lung volume. The amplitude, okay, so that's what you need to set, and we're going to go into these a little bit more on the up and coming slides here. Influences then the level of ventilation. Okay, so your amplitude is your power, also your power, and that's adjusted, there you go, by the power control. And what you're looking for to adjust that is chest wiggle. It's called the chest wiggle factor. It's a true thing. So that's kind of like the strength, I guess, of your breath. And then the frequency, again, it's in hertz, and a good place to kind of start is about 5 to 6 hertz. Though it has a range, I believe, from 3 to 10. There's an inspiratory time percent, which you usually have set at 33%. That's pretty standard, which then will give you an IDE of 1 to 2. And then there's a bias flow that's set from about 25 to 40 liters. So when are some times that you would consider using the oscillator? Patients with ARDS weighing at least 35 kilos who are not responding to conventional ventilation. When you get to that PEEP level of 10 or FiO2 above 60, and you're still only having a PaO2 of under 60. So about 60 for your FiO2, 10 for your PEEP, and you're still only having a PaO2 of 60, you might want to consider the oscillator. They are very successful in using it during the H1N1 flu outbreak. So who knows, maybe they'll find use for it with this new COVID-19. Patients that have air leaks, like from a chest tube, early intervention to recruit the lungs, so the earlier the better, before the damage has already been done. And unfortunate, that's kind of where it might get like a bad rap, is how I feel, is that a lot of these more extreme uses of ventilation, the different types, APRV and the oscillator, nitric, that you find that they don't use until it's kind of late in the course of the disease, or the ARDS. So if we can kind of jump on this and kind of get going with it a little bit sooner in the process, we might have a little bit better success. So a lot of physicians, hopefully, as times are changing, hopefully people have getting a little bit better understanding, being ready to take the risks. That's why we're educating you on it, to be a proponent for it, so that we're not using it as a last-ditch effort, where chances are the patient's going to expire anyway. Let's try to jump on a little bit sooner than later. All right. So when do you not want to use it? Okay. There's actually really no contraindications, I guess, for the 3100B. There's precautionary use. So this is kind of where, the benefits outweigh the risks type of thing. Okay, unstable cardiovascular status, because again, you're increasing that mean airway pressure, so you could, decrease your cardiac output. Severe or acute bronchospasm, severe acute bronchospasm, I would say. You might have some difficulty, but maybe once they get over that acute phase, where you're allowing the steroids and bronchodilators and stuff to kick in, it could be considered, or maybe using it with nitric. Severe acidosis, just mainly because a lot of times you find yourself in a permissive hypercapnia state, and these patients don't need to be any more acidotic than they already are. So if they're already severe acidosis, that might not be the best choice for them. I know that Marty did say that that one of the patients that they did use for the H1N1 crisis, they actually were pregnant. So again, depending on how far along and the complications of your blood flow and stuff, you don't want to compromise the fetus, the baby. COPD or asthma requiring the use of aerosolized bronchodilators, so they're probably not going to be distributed very well that way. So, all right. So, like I talked about before, it uses this piston to basically push and pull out gas. Okay. It's a diaphragm-shaped piston that's magnetically driven, and the gas then is oscillated back and forth by the action of the movement of the diaphragm, and that's what helps determine the tidal volume. Okay, so different things. How do we look at where to start with these patients? So bias flow is actually one of the first parameters that you set. Okay, the typical range is about 25 to 40 liters per minute. Setting the bias flow affects your mean airway pressure, okay, which influences your oxygenation. The mean airway pressure is also an adjustment, but I want to talk just a little bit longer about the bias flow before we move to the actual mean airway pressure. So if the flow isn't set adequately on the bias flow, then your mean airway pressure can't be reached. So if you need to increase your mean airway pressure, you need to make sure that your bias flow is set high enough. Okay, kind of provides like the working pressure. It gives you the flow that you need behind it, kind of like back in the day with the working pressure on the servo. Because a low flow may actually result in an increase in PaCO2, from not enough flow to wash out the exhaled gas. Also be careful that it's not too high either, because that can dampen the active exhalation, because there's like a little diaphragm in there, another little small diaphragm, not the one in the piston, but another one in the circuit, and Marty kind of shows us that when we go see it. So if the bias flow is set too high, it can dampen that active exhalation and only allow the gas to remove from the circuit. Okay, and then therefore you have an increased PaCO2 and results in auto peep. So we don't want to have to do that. So when we are talking though about so we talked about the bias flow, now looking at the mean airway pressure, we would like to set that about 3 to 5 centimeters above the mean airway pressure on the conventional ventilator. So if you have, let's say your mean airway pressure is 20 on your regular vent, because it's probably going to be higher because you're probably kind of starting to max out your settings on the conventional vent, you're going to start at maybe 23 or 25, okay? Saying 25 to 30 is actually a fairly normal value. Max is about 45 to 60. So as we increase the map, the tidal volume also increases, okay? We're just providing more pressure there. And then you should leave it alone. That's one thing about the oscillator, that you don't want to be making a lot of changes really quickly, okay? They tell you just to kind of sit on it for a little bit. So, you know, wait it out for about 24 hours or so to see your results, because you're not going to see it as fast as you are on a conventional ventilator. Okay. All right, what do we set next? So next would be your amplitude or your power. Okay. So as the amplitude is increased, the pressure gradient then is going to change or increases, and that also results in an increase in tidal volume. So starting at the power at about 6 to 7, that ranges from about 1 to 10 on the knob. Okay, so keep in mind that's the actual knob, has those numbers on it. Okay. This is kind of explained on page 493, also in your textbook. Okay, so you want to get that. This is where you're going to adjust the power amplitude to get that chest wiggle factor. Okay, so you're looking for wiggle, basically. You're looking for it to kind of shimmy or wiggle back and forth, kind of rock back and forth from about the level of the clavicle to the mid-thigh on adults. Okay, so this may take then an amplitude of like 60 to 80. In the video that you're going to watch at the end of this lecture, the videos are geared for peds. It's like a 13-month-old patient. So also that is what controls the level. Also, if you have to, you can adjust this power level to mess with your PaCO2 if you need to too. Also, sorry, PaCO2 also. Any changes in your airway resistance, your lung compliance, and your ET tube size will also affect the amplitude delivery, so keep that in mind. So the other thing we need to set is the frequency or the hertz, okay? So you have to keep in mind that 1 hertz is equal to 60 breaths per minute, okay? So your initial settings then are about 5 to 6 hertz. So what is that? About 300 to 360 breaths per minute. So it really, it just sounds kind of like a jackhammer when it's running. It's just like boop, 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 boop. Don't laugh at me. I know you guys are, but whatever. And that's just kind of how it sounds. And it's like super fast. That's just in the chest is wiggling at that rate, and that is the hertz. Okay. So believe it or not, when you want to increase your tidal volume, okay, or increase your minute volume, you are actually going to reduce the frequency, because that slows the movement of the piston down a little bit, decreases the movement of the piston, okay, but it causes a greater volume displacement. So it's reducing the frequency of the piston, not so much, I guess, the strength of it, but the frequency of it, and it causes a greater volume displacement. Okay. So reducing the frequency causes a greater volume displacement, so a large tidal volume and a higher minute volume. Okay, so just like increasing the frequency would result in a smaller volume displacement and a smaller tidal volume and lower minute volume if you were to increase the frequency. Okay, so to actually decrease the PaCO2 on this particular machine, you would decrease your frequency to allow greater volume displacement. Okay. And then again, your inspiratory time, your I time, is going to be set at 33% to have an IDE of 1 to 2. So different monitoring, assessment, and adjustment, just kind of recapping a couple things here. Again, an upward adjustment in the frequency is going to result in an increase in your PaCO2, okay, because you're going to have a smaller volume displacement. And then a downward adjustment in the frequency is going to result in a decreased PaCO2. Another way to get rid of carbon dioxide is to actually have a small cuff leak, a deliberate cuff leak, okay? So when your amplitude, your frequency, your time percent, inspiratory time percent have been optimally adjusted and you really can't do anything else, and your CO2 is still high, you're going to have a deliberate cuff leak, and that might actually help increase gas flow through and around the ET tube and help eliminate the CO2. So of course, you want to make sure you're doing really great oral care, making sure your head of bed is up before you end up dropping that cuff or deflating the cuff a little bit. Okay, so we start looking at when do we think it's time to return our patient to conventional ventilation. So once this patient is stable with a mean airway pressure of about 20 to 24, your SAT's about 88% or more, hopefully a little bit higher to give you a little more leeway. FiO2 is less than 50%. You can think about switching your patient back to conventional ventilation. One of the things that they suggested was manually ventilate your patient with the ambu bag, and the old-fashioned way at 50% and about 10 a peep, and kind of see where their SATs sit. So if they're able to maintain their saturation while they're taken off the oscillator by bagging them at 50% at 10 a peep, then maybe it's worth a trial of putting them back on conventional ventilation. So these are a couple of the YouTube videos that I would like you to watch. Again, they do talk about pediatric use, a 13-month-old, because that's kind of where it kind of started its popularity. But I do want you to watch these videos and then post on the discussion board along with the APRV one, and kind of just give me like a big takeaway from it, just some type of a discussion or a point that you found interesting. Okay, that is part 1 of this day's lecture.